Greetings, everyone. I am Supanon Jamosoria and I will present the poster in the topic of molecular simulation for molecular and surface properties of random polyethylene copropylene copolymer free-standing film. My coworker is Ms. Jidapa and my advisor is Dr. Visit Vao-Soongnern. This work will develop the Monte Carlo simulation of coarse-grained model to investigate the molecular and structural property of polyethylene copropylene random copolymer as a function of ethylene content. So first of all, we make the coarse-grained model grouping either ethylene and propylene unit to one the coarse-grained piece. We then represent this coarse-grained chain using the rotational isomeric state model define the short-range intramolecular interaction. The statistical weight matrix for the PEPP copolymer was proposed by James Mark in 1972, containing 6 different methods with only 3 energy parameters here. And we adapt this IS model to our coarse-graining procedure on the mapping to the high coordination lattice in our simulation. To simulate the box system, we map the multiple coarse-grain onto the second nearest neighbor diamond lattice or 2NND lattice to improve the computational efficiency and use the less storage during the simulation. For multiple chain simulation, we introduce non-bond interaction using the lattice version of Lennard-Jones potential energy function. This is the parameter set of Lj potential for on a PEPP copolymer. The movement of bead is controlled by metropolis algorithm, which the move will be accepted if the energy chain becomes lower. If not, there is a criterion to prevent the local minima trapping by comparing the Boltzmann factor with the random number. Only the chain with small increasing energy can be accepted. Based on the metropolis technique, the system will be driven to equilibrium with lower energy state. To form polymer film, we extend the periodic box dimension in the z-axis about 3 times so that the original parent chain cannot be interact with its image. These are the simulation parameters. At figure 1, we show the snapshot of random copolymer thin film at the various ethylene fractions. Clearly, films become denser with sharper surface at higher ethylene content. Figure 2 is the relative density profile as a function of distance from the midplane of film. The density in the bulk region are relatively constant but significantly dropped near the surface. The profile becomes denser with a sharper surface for higher ethylene content. The figure 3 is a fitting density profile to theoretical function of polymer surface is shown here. As a function, ethylene content copolymer thin film are more condensed. Interfacial profiles are sharper and narrower the interfacial width. At figure 4, this shows the distribution of the chain center of mass, which has the similar trend to the density profile, but it can exhibit the oscillating pattern. Figure 5 is bond orientational order parameter. The S value equal to 0 is mean the bonds are randomly oriented, while the minus 0.5 and 1 mean parallel and perpendicular to the surface respectively. All profiles have similar trends. Copolymer chains containing more propylene beads have order parameter closer to zero. The bond orientation become more anisotropic for the copolymer chains with larger ethylene content. In figure 6, uh, the chains become more compact for larger ethylene content. Chain shape factor asphericity decreased in the direction toward the film surface. The result of chain flattening. This result related not only to the monomer content but also the confinement from impenetrable free surface. Figure 7 show that the molecular size or radius of gyration (Rg) in normal direction becomes smaller along the distance from the film center, and it was decreased in the region close to the surface. Figure 8, the largest molecular axes tend to orient parallel to the film surface, and the orientation becomes more isotropic for copolymer chain with less ethylene fraction. The system energetics are present in the figure 9. Higher intra-chain interaction is found, indicating more gauge conformation for the larger ethylene content. In Table 1, the three major axis radius of gyration ratio is shown here. Note that the theoretical random flight chain model predict ratio of this is 11.7, 2.7, and 1. And this is the summary of this work. So I would like to acknowledge my university, SUT Suranali University of Technology, and the DPST Scholarship Program. Thank you very much, and I am happy to discuss with you from my work. Thank you.